Before I start my today's lecture, let us quickly go through what I have covered in my previous lecture. So, I started my lecture with the definition of GIS. So, I hope you remember that topics which I have covered to you in the previous lecture. So, I am just going to highlight few of the very important aspect of that. So, here GIS allows to integrate many data in a single map, which enables to visualize, question, analyze and interpret data to understand relationships, patterns and trends more efficiently. So, this is the beauty of GIS, where you can integrate many or n number of data sets together and you can run a query that will give you some answers which are hidden in those data sets, right. So, we started with data, and then what is the difference between data and information, then information system, then digital information system. I hope you remember these figures. So, here basically this is very good information of a information system, where you can easily find out the information hidden in this telephone directory by just identifying the first letter of that word, right. And this is how we are going to access, or we are going to get our answers by sending a query to this information system, and this information system will provide you an answer, right. And this is one example of digital information system, where you can find the answers available to you through different modes or different places, right. So, here you are not going to manage this, you are not managing this, you are not managing this, you are not managing this. So, data has been captured and analyzed by others, but that is available to you through a information system. So, all these data sets are available to you in digital format. So, that is how this digital system or digital information system is in the picture. Now, the next component which I have highlighted in my previous lecture was geographical information system components. So, what are the different components we actually see in a GIS? So, first one is computer hardware, second is software, third is geographic data or the spatial data, and the last one but the most important part is to a person who captures, stores, update, manipulate, analyze, display these data set as a information. So, it is very important to note that here all these capture, store and update, basically this require group of peoples, not only one people. So, depending upon the size of the data or the quality of the data or what kind of data you are going to access, there are many individuals or many organization or many groups are involved in this one. So, that is how this geographical information system components are very important. So, none of them are insignificant, all of them are significant and they are playing critical role in this GIS. Data type, that also I have covered in my previous lecture. So, there are two different major types of data set. First one is raster, second one is vector. So, what are the difference? Raster is basically your images, right? Images where you have grids, pixels or elements, whereas in vector you have point, line and polygon. And there is a third type of data which is known as TIN, triangulated irregular network. So, in this one, this is basically considered as a different category. This TIN is considered as a different category, where we do not consider this TIN into either of raster or vector. So, this is third category of the data type. Now, this TIN is very important in generating the digital elevation model, or maybe the parameters which you have collected and you want to interpolate. So this triangulated irregular network is very nice. And the next topic which I have covered was attribute. So all these data set, raster, vector or tin, they can have attribute table attached with the main file. Attribute table may look like this, where you have many other parameters apart from FID and ID, right. So here you can use this table to interpolate or to extract the information what you want. Now the next component was topology, because when we are dealing with vector data, topologies play very critical role, because it defines the rule or behavior how these point, line and polygons are connected with each other, or how they share the geometry with each other, and what is the position and location of each individual line, point or polygon, whether they are inside or whether they are sharing the boundary or whether they are just overlapping each other. So those information can be stored when we have this topology, right. A typical GIS structure was also discussed in previous lecture, where I have shown you a flow chart like this. In GIS, basically we start this flow by defining the problem. So first step will be define your problem, then define GIS criteria which can help you to achieve this particular objective, right. And then third will be import or build data, and that will be from different sources. GIS analysis, because you have already defined the criteria, so here you will perform the analysis, and at this stage you will receive your output or the result. Then you have to analyze them and you have to make a decision if it is for a early warning system or any such application. So this was the flow which we have discussed in my previous lecture. I hope this is very clear, and you can use this flow to define your problem, and then you can work with GIS and remote sensing. After that, I started explaining you the different spatial functions which is or which can be done in GIS environment. So to continue with that topic, let us start with the interpolation. So interpolation is a method of approximating set of values distributed over a space if some values of the set are known. Interpolation can be used to estimate elevation, rainfall, temperature, chemical set dispersion or other spatially based phenomena. So basically here you have two values and you want to derive this particular point value, or what will be the value at this particular location. So this is known as interpolation. Interpolation can be performed on vector using a tin surface model. I hope you remember the tin, triangulated irregular network. So here basically this is in simple words what exactly we do in interpolation. So here you have A and B, and the value of A is 87 and value of B is 129, and I want to calculate the value of C, and with this is unknown. This is after calculation. So how do we exactly know that this is the value of point C, and which C may not be at the center of this A and B. So what we will do, first we need to divide it into different units. So here distance between A and B is 45 units. This you have to calculate. Then to find the value at an unknown point C at a distance of 20 unit from A. So this is basically 20 and here you have 25. That means the distance is 45 between A and B. At a distance of say 20 unit from A, value of C can be calculated like this. So this is very easy when you are having only 2 points and you want to calculate. So you just have to estimate the distance and divide the values into different segments and then you can easily find out what will be the value of C. So, this such operation can be easily done with the GIS, where we have location attached. Now, here this is another example. So, this is the image. So, let us say you have one value here, one value here and one value here, and you want to calculate for this particular location. So, how you will do that? Similarly, like we have done in the previous slide. So, you have this triangle. So, A, B, C, and the A and C is having a point D, which is at midpoint. So, here it will be very easy. So, D is equal to A plus C divided by 2. So, just half of the A and C, right. These are very basic operation of interpolation. Now, let us see what else we can do in interpolation. So, spatial interpolation depends on two major factors. So, first one is you need to have known points. Without that you cannot do, or you cannot perform interpolation. So, sample points with known values in space. Spatial interpolation scheme or type. So, what scheme or type you are going to follow while performing this spatial interpolation. So, here you have spatial interpolation, and it can be done by global interpolation or local interpolation. So, in local or global interpolation, what exactly we do? Let us see here. So, in global interpolation, every known value is used to determine an unknown value, whereas local interpolation, a set of known values are used to determine an unknown value. So, this is the basic difference between global and local interpolation. Spatial interpolation can be of two different types. So, first one is deterministic and second one is stochastic. So, in deterministic, basically no error assessment with determine unknown values, whereas in stochastic, error assessment with determine unknown values. So, this is the basic difference between stochastic and deterministic, and accordingly you have to choose which method you want to perform or apply for this spatial interpolation. Now, the next one is global interpolation technique. As I told you, we have two different techniques. Either you have to perform global or local interpolation technique. So, let us start with the global interpolation technique. So, here we have the first one, which is known as trend surface model. It uses a polynomial equation to approximate points with known values, where you can use this polynomial equation and you can easily find out what will be the value of unknown point, right. So, here the z is a function of x and y, b0, b1, b2 are coefficients and can be obtained using known points in the equation. So, I hope you have understood this part, because this is the basic or fundamental polynomial equation. You can use here, or you can increase the level of polynomial equation here, or the degree of polynomial equation here, so that you can achieve more accuracy. Trend surface models are computationally complex and inexact interpolation technique. So, this is the continuation of this trend surface model. Now, let us see what other method we can apply in the global mode. So, here we have regression model. So, regression, I hope you are familiar with regression. So, because in maths we generally use this regression, polynomial equations, right. So, in general it is used to examine the influence of one or more independent variable on a dependent variable, and in interpolation it relates dependent variable in a linear equation that interpolates and then can be used for estimation. So, that is the advantage when you are having this regression model as your interpolation technique. Now, for the local interpolation technique, we have density estimation. So, it measures cell density in a raster by using a set of known points. a neighborhood is defined around each raster cell and the number of points that fall within is totaled and divided by the area of neighborhood. So, again here you have to correlate with your satellite data where you had pixels. So, what it says is cell density in a raster by using a set of known points. So, the cell density means what is the value which you are looking for, that density you have to estimate by using the known location or the known values. A neighborhood is defined around each raster cell and the number of points that fall within is totaled and divided by the area of the neighborhood. So, this is how you have to apply this density estimation. Now, the next method is Thiessen polygon. So, Thiessen polygon is one of the popular method in interpolation, but it is little bit complex than other. So, let us see how exactly you can perform this. So, it assigns interpolated values equal to the value found at the nearest sample location, right, also called as nearest sample or nearest neighbor technique, because it is going to take the immediate neighbor value. So, it is more accurate. Relatively simple method where only one point is used, right. Now, let us see how exactly we perform this one. So, you have some set of points. So, input point coverage. So, all these points values are known. Now, what we will do? We will connect all the nearest elements and we will make the triangle. So, that will give you TIN, triangulated irregular network, and then we will identify the midpoint here and we will draw a perpendicular. So, that will be bisected TIN, and you can see here for all the points we had this sides and where we have dissected, and this bisected TIN is going to be the sides of your Thiessen polygon. Now, what you have to do? You have to extend them and you have to join them, right. So, that will look like this. So, here you can see this is the value for this particular polygon, this is the value for this particular polygon, this is the value for this particular polygon. So, it is expected that your output or your result will be more accurate than other values or other methods. Why? Because it works on the nearest neighbor concept. Now, the next is IDW, inverse distance weightage method. Now, slowly it is gaining its popularity because this is giving you more accurate data. It works on the condition that the estimated value of a point is affected more by nearby known points than those lying on the farther distance. Here you can use this particular equation to calculate this inverse distance weighted. So, where Zk is the estimated value, Zi is the value of known points, Di is the estimated distance of known points, and I is the number of points and K is the known power. So, basically if you have 4 or 5 or let us say these points you have which you want to interpolate by using this inverse distance weighted method, then if I consider this and this particular point, these 2 points, and if I take the average or if I take the just divide it and if I estimate the value of this particular location, this may give you good result. But what if these 2 points are connected and you are going to use these value to calculate the value for this particular location? So, it may be wrong. Or in another case, let us say this and this value are lying very far from each other, right? And there is one more value here. So, if I say if I want to calculate the value of this particular point, then if I use this relationship or this relationship which one should give more or better result. So it is expected that the weightage of this particular point should be more on this particular location. Why? Because it is near to this position, right, or near to that place. So that's why we have started thinking towards this distance weightage. So as the distance is decreasing, the weightage will increase. As the distance is increasing, weightage will decrease. Now the next method is kriging. It is a geostatistical method of spatial interpolation. It uses a semi-variance for measuring spatially correlated components. It measures the distance between all possible pairs of sample points and model the spatial autocorrelation for the particular surface. Basic kriging methods are simple kriging, ordinary kriging, universal kriging, and so on. You can search for this. Now we have next method, which is known as spline. So spline is one of the best method if you want to perform a smoothing effect on the spectra. Spectral measurement, hope you remember from hyperspectral remote sensing section. So because when you acquire a spectra, or when you take a spectra from library, right, so the acquired spectra may have this kind of behavior. So but this is because of some noise which has been introduced either by instrument or maybe different topography or illumination condition or atmosphere. So basically we want to remove this particular effect. So for that we need to have some method which works well on the smoothing of such a spectra. So for that we have a spline. It creates a surface that passes via known points and has the least possible changes in slope at all the points. It creates a smooth surface that passes via known points and has the least possible changes in the slope at the point. Spline can be performed using this equation, where x and y are coordinates of point to be interpolated, and di square is basically square of x minus xi plus square of y minus yi. So this can be used to perform or apply the spline or the smoothing on any given data. There are two different types of interpolation in spline. So first one is regularized and second one is tension spline. Here you have flexibility to apply this spline with barrier. Now let us understand what is the concept of barrier in interpolation technique, because if you use IDW or kriging or spline, everywhere you can apply or you can use this barrier. Why? Let us understand this. So let's see, you have this point data, right, and which is maybe x parameter. Now this x parameter, you want to perform this interpolation and you want to generate a value for each and every pixel or location of this map, right. So for that what we will do, we will run the spline or maybe IDW or maybe kriging, but if you see, all the data sets are actually concentrated in this particular location. So if I do interpolation for this area, whether this will be correct? No, because this will again get changed to extrapolation. So instead of interpolation, you will end up with extrapolation, and extrapolation value or extrapolated values are not correct. So here what we will do, we will define this boundary that all the interpolation, whatever method you are going to use, it should run only within this particular boundary. So that's why this is known as spline with barrier. So here it says interpolates a surface using barrier from points using a minimum curvature spline technique this barrier are entered as either polygon or polyline feature that I have already explained to you. Now the next one is trend. So you might have heard about trend analysis. So this is just part of that. It uses a least square regression to fit a surface over the known sample point. Surface is constructed with the notion that the difference between actual and estimated values is as small as possible, but the surface rarely passes through the input points, which make this technique inexact. So that's why you have n number of techniques, but you need to understand their advantages and disadvantages and what is the utility of that method in your application. Accordingly, you have to decide your technique. So in case of trend, it is a good for identifying coarse scale pattern in data. So in case if you want to perform the coarse resolution data analysis or where you want to perform the interpolation, then this trend method will give you good result. Now coming back to GIS. So in GIS, a very important objective is data visualization. So how do you visualize your data or how do you prepare your result that makes your analysis more strong? So here you can see this is one of the map prepared in GIS environment where you can see different layers are integrated together and you can see all the elements of a map. So here you have north and south arrow. This is your scale, these are the legends, and here different colors and textures are used to highlight different components of this particular map. So let's understand more about this map in GIS. So here it is an informative 2D representation of 3D space, that is the definition of a map. So we want to present our real world pictures or objects in 2D, right, on a plain paper. So it can be a hard copy representation on a sheet or digital representation on a screen. So both are basically map. Basic map characteristics tell the user what the object is and what is the object or attribute. So instead of writing all the values like it is high or low or medium or moderate, you can use different symbol, different texture or different way of representing your data. So that is the beauty of your GIS environment. Map are equipped with scale that you have already seen, legends, and are defined onto a projection that helps in visualizing the curved surface of the earth on the flat surface of paper or screen. So this is very important as we are working in GIS. So spatial data is always there. So spatial data means where you have latitude, longitude or a location value is attached, right? So here how do we define or how do we say this is the location of this particular position or object or material? So we need to have some kind of a standard, so that we will see slowly what reference we are using, why we are using. So those things we will cover in this lecture. Now let us go with this map. I hope you remember my initial lectures where I have explained the analog and digital photograph. So here you can see this is the analog map where all the object or materials have been highlighted by using different colors. So this anybody can prepare, right? But when we are talking about digital map, you can see here, so all these areas have been captured by a satellite where elements, the smallest element of this particular map will be a pixel, right? And when we are involved in remote sensing from space or maybe airborne sensor, then we have one DN value, and with this DN value you have latitude and longitude. So these three values will be there in your data. So that gives the strength to this GIS where we always consider spatial data. So, spatial data should have latitude, longitude or some location values. So, map in GIS environments are used for digitizing, scanning of existing map. So, in case if you want to generate a digital map from a analog map. So, let us consider you have visited a field and you have drawn some features and with the location values measured by GPS, and that you have produced in a hard copy. Then I need not go and visit that place, I can simply use your map, I can scan it and then I can georeference that map using the latitude, longitude measured by you, and I can produce the digitized or scanned map, right. And if you have a raster map where you have all these different objects, where in GIS you have a flexibility, you can overlay a vector layer here and you can make a polygon by tracing these features. So, ultimately you are going to reproduce this result in vector form. So, that is known as digitization. So, by digitizing you can convert this raster data to vector data. In raster data you have pixels, in vector data you have point, line and polygons. Next one is querying map. So, considering you have 10 different layers in GIS environment, where one component is let us say population, second one is available drinking water, third one is available shopping mall and fourth one is what is the rent in that particular area. So, if you have all this information, you can easily find which place is good for you to find a new home, right. So, you can just run a query, show me very good drinking water quality or the available drinking water plus low rent plus less populated area plus available marketplace. So, that will give you a result or that will highlight a location where you can simply go and find your new house. So, this is one of the example how we can use this GIS for our day life problems. Display the results of remote sensing and GIS operation. So, as I told you, all the maps which has been generated using a remote sensing data, that has to be undergo through this GIS processes, right. Execute and support visual analysis, and remember maps are not only the final products, there are many other forms through which you can generate the result in GIS environment, right. Now, let us see what are the different characteristics of a map. So, map provides answers to questions related to basic components of geographic data. So, basically this is in your graphical form. So, this can give you geographic location and it can have this thematic attributes like what is the population distribution in a particular area, what is the groundwater depth in some cities, what is the air pollution level. So, those things if you have as your theme and you have a output in form of map, they are known as thematic maps. Then time. So, time is also one important parameter. So, whenever you are producing a map, the time stamp should be there. Why? Because that says these parameters whatever I have used in my map generation, that has been captured at particular location and point or time, right. So, let us see what exactly this geographical location means. So, here you can see this particular map where you have latitude and longitude written. So, if you want to find out what is the location of this particular point, you can easily find out by just extending these lines, and you can find out what is the value here, what is the value here, and then you can always find what is the location value for a given or for your study area or for your object or material. So, here it refers to location of a place on the earth defined by latitude longitude. Longitude denotes east-west position of a geographic location, runs north and south between two poles. Prime or Greenwich meridian is assigned 0 line for longitude. Latitude denotes north-south position of a geographic location, also called parallels and run perpendicular to longitudes. Equators is assigned 0 line for latitude. All latitudes are parallel to each other. So, these I have written in very layman language, so you can easily understand what exactly this latitude longitude means and how they are varying. And remember, they are perpendicular to each other, so they have variation in different direction from each other. Then when we say thematic maps or thematic attributes attached to a particular map, what exactly it means? So, it refers to a particular theme like rainfall, temperature, human characteristics like population, health, etc. of mapping. So, here this is one example. This is the example of thematic maps. So, here this is annual mean temperature map of India, right. This is another annual mean rainfall map of India, and this is elevation zone map of India. So, these are thematic maps because each of them are having different theme or different information. So, in the next example, we have this 3 maps, and you can see in 1992 and 1988 how this river was behaving, whereas in 2002 and 1988 how it is behaving, and with respect to 88 in 2014 how it has changed its course. So, this basically explains how this particular river is meandering. So, here basically again it explains the theme. So, this is related to hydrogeomorphic problems. So, here if you have such information, you can predict or you can extend this behavior of this river to predict in which direction it may shift in coming 5 years. Now, the next important parameter in your map is time. So, let us see this one at Jan, Feb, March, April, May, right, how this area is getting changed. So, the seasonal behavior is also very important when you are involved in agriculture, forestry or water related problems. I hope by now you are familiar with this standard false color composite. So, this red color basically represents the vegetation in your study area. So, here you can see how this red color is changing through all these years. So, this gives you very important information about your problem through the time. The next important parameter of this map is how do we represent our values. So, in case if you have population data for Guwahati city or maybe Delhi, how do you represent it? The next very important parameter of this map is visualization of the value. So, how do you explain or how do you represent the densely populated areas or very less populated areas in a single map? So, you need to use some convention so that people can understand or I can understand, you can understand how these values are changing with different places. So, map offers abstract representation of reality. So, first one is simplified, then classified and then symbolized. So, all these 3 different types you can use to represent your data in a map. So, maps are representation at scale that already you have gone through. I have explained you all different types of scales in my lectures. Now the scale is basically ratio between distance on the map and corresponding distance on the ground. So here I am talking about this scale of this map, right. So here you have a map and this is the scale where it says 1 centimeter is equal to some x kilometer or meter. That means this particular scale can be used to identify or to measure the distance between two places or the other geometric parameters within this particular map. So how this is going to help you when you are having all the digital data. So basically here this scale is important when you are going to print this particular map and you are going to keep it for few years. So after 5 or 10 years what will happen? The paper will shrink and then simultaneously this scale will also get shrunk. So then this scale and this map is shrinking together. So this scale can be used to identify even after 10 years or 20 years. So that's why we always put scale bar in our output map. Next important parameter is how do we represent our data. So you can use some shapes to symbolize different parameters within a map. So here you can see for a given area you have this and this. So all these things will be listed in your legend. So what exactly star means, what exactly this circle means, that will be there in your output map. So it is good for qualitative representation as each shape symbolizes a specific type. Then you can use the thickness of the line, that also helps to represent your data. So this is also for a qualitative differences. Now the next is color hue, where you can use this different colors or different intensity of the color, but here not only one single color in different intensity, that will fall under next category. So you can see here this is also for qualitative analysis. Then color value, here you can use to represent your quantitative data. So like this may be 10, this may be 20, or in scale you can put how it is changing, right. The next is color intensity. So the color intensity can also be used as the previous one. So where I have shown you different scales. So here you can also put a scale of a single color, and this you can use for qualitative or quantitative also. Next one is texture. Because why I am telling you all this? Because whenever you are preparing a map in GIS environment, you may have n number of input data sets. So you have to highlight all the parameters coming from different maps in your output. So for that you may need different types or different convention to highlight all the parameters, and that should be independent from each other. So there may not be any doubt between this and this. So immediately if I see this color and the legend, I should not get confused with this. So if you are using this texture, you can use for both qualitative and quantitative data. So this is summary. So you can see the shape can be used for qualitative, size you can use. So the bigger size may represent high population, or the high or the very bad air pollution level, and this may be the lightest one, may be safest zone, this may be the danger zone. So depending upon your application, you can use all these convention or all these different types of shape, size, color intensity, textures to represent your data in a map. So here this is one of the simplified map. This is classified and simplified. So you can see all these data sets. So in symbolized and classified, you can see this result, and I hope you remember my classification technique lectures. So this is basically coming from there. So all these colors will be listed in your legend, and each legend will explain what parameter or what class you are representing with this particular color. Now let me ask you one question. You might have seen this kind of figures in internet, right? So whether this is a good representation or bad representation, or whether it is a good representation of our earth, yes or no? So I will give answer. So that is no. Forget about all these boundary conflicts. So I am not going to use this as any country specific. So here just I wanted to show that if you put some colors or textures, that doesn't mean it is a map. Now you see this particular map. What do you feel about this? So here you have some more information from the previous map. So here you have location, which is in the form of latitude, longitude. So definitely this map is better than the previous one. Here you can easily find out the position of any given location, right? So this kind of representation is expected in your output map. So let's see what reference system we are following to represent this whole world in latitude, longitude, because there should be some convention by which we are identifying a particular location or position. So for that we always refer our earth as a spheroid or ellipsoid. Let's see, when we consider our earth as a spheroid, what happens, and when we consider it as spheroid, what happens. So spherical earth model represents the shape of the earth with a sphere of a specified radius, right? You might have seen this kind of figure many places. So here basically this gives you the latitude, and this is the parallel. So and this is equator. So how it is moving? It is shifting from here to here, or how it is varying in this direction, whereas this is varying in this direction, right? So spherical earth models are often used for navigation and for global distance approximation. May be used for coarse scale map, because as we know our earth is not a spherical model, right? So it has to be different from sphere. So that's why we have shifted ourselves to ellipsoid, and where this is actually best representing our earth, where we have this prime meridian, you can see here, equator, longitude, again it is coming in this direction, right? So it requires for accurate range and bearing calculation over long distances. So this is more accurate when we are considering spherical earth model that was used for global approximation. So very coarse scale map can be generated, but when we want to find out very minute or very small places and exact location of that, then we should go for the ellipsoid. So the radio and GPS navigation receiver uses the ellipsoidal earth model to compute position and waypoint information. So let us see, when we consider earth as ellipsoid, what parameter or what are the details we consider in that. So ellipsoid is a 3D figure obtained by directional scaling or affine transformation of a sphere. The best of these models can represent the sphere of the earth over the smooth average sea surface to within about 100 meters. So you can see this particular figure. So this is our earth, and these are the pole and equator, and when we see semi minor axis and major axis, so basically the major will have the greater value. So if you see which one is minor or major, suppose this is your ellipsoid, so this is your semi minor axis, and here this is your semi major axis, right? So in this ellipsoidal model, it is very important to estimate the flattening. Flattening is a measure of compression of a sphere along a diameter to form an ellipsoid, and eccentricity, that is E, is measure of how much the conic section deviates from being circular, right. So flattening can be calculated using this formula, and for WGS-84 value, this is the given value, right. And eccentricity is basically 2f minus f square, and the WGS-84 value is this much. If you want to understand more about this ellipsoid, let us understand about the topography and what are the mathematical surfaces we are assuming here. So this is the topography. So I hope you are able to see this. So this is basically your topography. Now this is known as a small h, and this is the semi-major and semi-minor axis A and B, and this is the geocenter. So this is the reference ellipsoids are identified by semi-major and semi-minor axis. Now here again, this topography you can assume here. So this topography so small h you are familiar with. Now when we consider our earth as ellipsoid, still it is not getting fit with this particular topography. When we consider this ellipsoid to represent our earth surface, so this is not fitting with our topography. So for which we need an additional imaginary ellipsoid which can represent our topography in better way. So for that, if you can draw this kind of ellipsoid here, that may give you better fit than this global ellipsoid. So that is the benefit when you are having local ellipsoids. So for all the countries, this local ellipsoids are different. So when you are having more undulation, your local ellipsoid size should be very small. There is another important concept in this GIS, so that is known as geoid. The equipotential surface of earth gravitational field, which would coincide with the ocean surface if the earth were undisturbed and without topography. So that will exactly match with your sea surface. Geoid model attempt to represent the surface of the entire earth over both land and ocean as the surface resulted from the gravity alone. So here the gravity is same throughout this geoid line. This is what was highlighted here, the gravitational field which would coincide with the ocean surface. That means this is the equipotential gravity line. So here if you see, there is the topography, right, and you have a ellipsoid here, and this will be the geoid. So doesn't matter which ellipsoid you use, it cannot be better than your geoid, because geoid can pick up the local variation because it is based on the gravity. So this ellipsoid and geoid both are important to represent or to model our surface, and then we will ultimately use some referencing system to identify a given position. Here if you see, let us assume this is the topography here, and here you have equator, ellipsoidal surface, and this is the point for which I want to measure the height. So, that reference will be from geoid, because the sea surface label is our base label, right. So, if you see the major and minor axis here, so the major is A and minor axis is B. Now, here if you draw a line or perpendicular, you can see here this is your H, which I expressed in the previous slide. So, here if you know, this is the H and this is the latitude and this is the longitude, right. Now, how do we use this particular concept to identify a height for a given point? So, I hope you are able to see this particular topography here. Now, this is the ellipsoid and this is the topography, right. You can see these lines. Now, I want to estimate the height for this point P, and the distance between the ellipsoid and the point P is small h, and this is the geoid. So, from geoid again you may have this height. So, from ellipsoid you have small h, from geoid you have capital H, and the distance between geoid and ellipsoid is capital N. So, you can use this particular equation to estimate the orthometric height. So, this H, which is basically from the geoid to your position, that is your orthometric height. Small h is basically from your ellipsoid, and capital N is the distance between your geoid and ellipsoid. So, this is known as geoid height. So, geodetic height is the height of a point on the physical surface of the earth above or below the ellipsoid, measured along a line that passes through the point on the earth and is normal to the surface of the ellipsoid. So, this is what we have seen here. So, this was related to the height estimation of a given point using this ellipsoid and geoid. So, that is all for today. Thank you.